Everyone, and thank you for attending today. Welcome to Introduction to Astronomy Research 2021, week 4. Very excited to bring to you another selection of tutorials and mentor profiles. On today's agenda, we have a tutorial on NASA's TESS mission led by Faye. We have a discussion of how to use Overleaf, which is a tool used to produce nice LaTeX documents used all the time in astronomy research. It's nice and shareable, and it's super handy in a lot of different ways. And that's going to be led. That discussion will be led by Priya, and then the paper discussion will be led by Anamitra, and that's going to be on exoplanet size distribution. So we have a lot lined up for you today. Should be really exciting. And without further ado, I'll hand off to Faye to get us started.
All right. Thanks, Howard. Hi everyone, have everyone had a chance to check out the video on TESS? Let me just briefly recap some of the key points. TESS stands for the Transiting Exoplanets Array Satellite. It was built by both NASA and MIT. And it has been the workhorse in discovering thousands of transiting exoplanets since its launch in 2018. But before talking about TESS, I think it put things into perspective if we talk about Kepler first. So in many ways, Kepler was TESS' predecessor. Kepler was an extremely successful mission. The vast majority of confirmed exoplanets were discovered by Kepler, actually more than 2,600 of them. And Kepler was launched back in 2009. Its main mission was to quantify the occurrence rate of Earth-like planets around sun-like stars. So to achieve that goal, Kepler mostly stared at a very small patch of the sky for several years. The hope was to catch a few transits of those Earth-like planets on yearly orbits around sun-like stars. So this strategy resulted in a very limited sky coverage. The Kepler mission missed out on a lot of nearby bright stars that are more amenable to more detailed characterization, such as radial velocity mass measurement and atmospheric studies. So the TESS mission was conceived. TESS is a nearly full sky mission so that it can review the closest, brightest planet host. And in this figure, we can see the Kepler field of view as a brown small patch in the upper right. It covers only about 0.5% of the night sky, whereas the TESS mission covers almost the entire night sky. So another point I should make is that one key result from Kepler is that closing exoplanets, those with orbital periods of around 10 days, are extremely common in our galaxy. Their occurrence rate is almost out of unity for a sun-like star. So TESS only needs to observe one patch of the sky for about a month before moving on to the next patch. And usually 1 month is good enough to detect many of those closing exoplanets. So the TESS spacecraft has 4 10-centimeter lenses, and each of them cover about 24 by 24 degrees of the night sky. So most of the night sky will only have 27 days of TESS data. However, the ecliptic pole, which will have continuous coverage up to about a year, these regions will enable the discovery of longer period planets. And this also happens, well, it is designed to overlap with the continuous viewing zone of the JWST telescope. Some additional details about the TESS mission. TESS will observe something like 200,000 nearby stars with 2-minute exposure time, and millions, if not billions, of other stars with 30-minute cadence. TESS is in a so-called high Earth orbit, which is in a 2-to-1 resonance with the lunar orbit. This orbit avoids obstruction of the telescope from both Earth and the Moon. As I mentioned, the spacecraft have 4 lenses. Each of them is 10 centimeter in diameter, and the wavelength coverage is 600 to 1,000 nanometers. So now let's check out some of the planets TESS discovered. So the first site I want to show you guys is this so-called Exoplanets website, and we will provide the link later. Here, all the TOIs, so-called test objects of interest, actually more than 4,000 of them are listed here. And you can click on them to bring you to a more detailed page for each object. For example, this one is a known planet, WAS46b. You can see various basic details of the host star, its coordinates, galactic coordinates, proper motion, etc. You can also see the properties of the planet, its orbital period, inclination, radius, mass, if it is known. Yeah, so I think this will be a good playground for you guys to check out some of the planet TESS has discovered. Yeah, and this will be a very nice resource for you to complete the tutorial, which asks you to identify a few test planets that you consider most interesting and plot their Lightkurve. So the next part of the tutorial, let's look at how we can download and play around with the TESS Lightkurve. So I should mention that this tutorial is almost entirely from the TESS Lightkurve tutorial written by Geert Ernsten. And this is a rather short version of it that shows us how to access and analyze test data. And we will also take the chance to look at the first test planet, Pymense B, or Pymense C. The B planet was actually discovered first from ground-based radial velocity survey. So this planet was identified in an earlier paper by Huang et al. 2018. If you're interested in more details of the system, you can check out the paper. So without further ado, let's take a look at the Lightkurve. So to install Lightkurve, I think by this point, many of you guys are pretty familiar with the pip install command. Just type it in any of the terminal, and you can then import the Lightkurve package. Let's do it here.
Hey, Faye?
Yeah.
You're sharing your whole desktop. Can you either make it full screen or just share your browser?
Oh. Is that big enough?
That's better, thanks.
Thanks. All right, so we were at the first cell, importing the Lightkurve package, NumPy package, also doing the matplotlib. And the first line here, actually downloading the so-called target pixel file. We will see what this means later. You can, the third cell, you can see this is actually showing you which mission the data belongs, the test mission. And one key number for identifying test objects is this so-called TIC number, or test input catalog. This is a pretty comprehensive effort to assign point sources on the sky with a unique number so that you can access them with just knowing the number. All right, let's plot the target pixel file. So what you can see here is the x-axis and y-axis are basically column and row number for the pixels on the spacecraft CCD detector. And the color coding are the amount of photoelectrons the detector has detected for that particular star. And you can see the star is no longer a point source here because our spacecraft or lens typically has some point spread function that spreads a point source into a non-zero spatial extent. Sometimes a Gaussian, but for realistic lenses, the shape deviates from a Gaussian. And you can see here it's not symmetric in the 2 dimensions. So what we can do to generate the Lightkurve is we put on something called aperture masks. So this is basically a selection of pixels we consider that belong to the point spread function of the star. And you basically what you do is sum all the fluxes within this aperture and consider that to be amount of flux that's coming from the host star. So this is a default aperture the test team uses. as you can see, it actually missed out on one of the pixels that's actually pretty bright. So something else we can do is we can compute the median of the whole aperture, of the whole target pixel funnels, and we can set some threshold, for example here 85%, and any pixel brighter than 83%, we can consider them as being part of the whole star. You can see this new aperture, which is slightly larger, actually encompasses most of the photoelectrons from the whole star pretty well. All right, so this is the 2D distribution of the light from the whole star. Now let's look at the light curve, which is the variation of the amount of light as a function of time. And you can do this by calling the two Lightkurve package, two Lightkurve function within the package. And this is basically it. The x-axis is time in barycentric Julian date minus some zero reference point. And the y-axis is the amount of electrons you see per second. And the data points are shown here. You can see the data points are pretty ready. There's a lot going on, for example, here. I suspect that's some instrumental effect rather than the whole star's intrinsic variability. So in the tutorial, in the assignment later, you will learn how to clean up the Lightkurve using functions built into Lightkurve, the package. All right, so the next step we want to do is actually see if we can recover the transit within this very poorly detrended data. So what we do is we go to Huang et al., the paper, and we find the orbital period and the time of transit, which we call T0, from that paper. And the period is actually 6.2679 days. And this is the 0 point for the transit, i.e. a reference point when the first transit occurs. So we can do that. And we phase fold the Lightkurve, which is just taking the modulus of the Lightkurve time axis by the orbital period of the planet. And we also shift the whole graph to the 0 point, so that transit actually occurs at phase 0. And you can see by eye, here the flux values near phase of 0 actually are lower than the other flux values. And this is indicative usually of a periodic transit that repeats on this orbital period. So for assignments, I want you to pick another system that you consider interesting using the Exoplanet archive. Download its Lightkurve from the MAS website using the Lightkurve package. And in part 2, you can clean up the Lightkurve using functions built into the Lightkurve package. And you can do something called the Boss least square method, which is typically what scientists use to discover periodic transiting planets. So by that point, you will probably reproduce, well, roughly 50% what the TESS team do with their data. I think it will be a rewarding experience, and you'll see it's actually not that hard. Right, I think that's it.
Thank you so much, Faye. That was just great. While we have the other discussion coming up next, if people have questions about TESS Lightkurves, they can feel free to put them in the chat and get them answered in semi-real time. There's one question real quick, Faye. There's Box least squared method refers to the linear algebra process. Is that correct?
So, well, I'm not sure it's linear algebra. So all it does is doing a grid search of orbital periods, transit duration, and phase, which is T0. So what you do is you take your Lightkurve, phase fold it as a trial period, and shift the time axis to T0, and you consider a range of transit durations, usually on the order of a few hours. And the single question you ask is, are the flux within the transit duration actually lower than the flux outside the transit duration? If so, the false least square summary statistic is going to be high. And you can do this throughout for different orbital periods, and you can identify the peak period.
Thanks, Faye. There's another question that says, is the median method to set aperture recommended when there are other bright sources in the target pixel file?
Very good question. So if there's confusion sources, this definitely does not work. But a good thing is that for many of the few stars, they are well separated. Usually the point spread function is smaller than their typical separation. If it is not the case, then you have to do something more complicated. For example, point spread function fitting. So you know what your local point spread function is going to look like, and you can fit two of them for nearby stars and figure out which are the flux coming from which of the star.
Thanks, Faye. Thanks for those questions. I'm just going to flash this up on the screen really quickly here and hand off directly to Priya for a discussion of Overleaf. Take it away. Thanks again, Faye.
Yeah. Thanks. So hello everyone. I'll be talking to you about Overleaf, and Overleaf, as you see, is your online text editor, and it's like Howard mentioned, it's a very useful tool which is used by everyone, and we'll see what it's all about. So what is Overleaf? Overleaf is basically a collaborative cloud-based text editor, LaTeX editor, used for writing, editing, and publishing scientific documents. It partners with a wide range of scientific publishers to provide official journal LaTeX templates and direct submission links. So basically, what does that mean? That sounded very complicated. So what does that mean in simple words? In simple words, that means that you can, if you have LaTeX files, you can edit your LaTeX files from any device that connects to the net. No need to have it installed. So for example, you can use your smartphone, you can use whatever you have, and you need not worry about what version of LaTeX do you have installed and how, whether it's compatible with various features, etc. Because this is a common LaTeX which you're using, which is online. So it's much more comfortable. Overleaf also, I will be demonstrating that to you all, but it basically has various beautiful templates that can suit your requirements. For example, next week you all will be making a CV. So you'll see how, for example, there are various templates available for CVs on Overleaf. Along with that, there are templates for specific scientific journals. Their templates are also available over there. If you want to do presentations, right, instead of PowerPoint, you can have a LaTeX presentation, and for that also there are various templates available on Overleaf. If you have a conference poster you want to present, there are a whole bunch of templates available which you can use. Then the other advantage is that you can, this is a very strong point about Overleaf, is that since this is online, if you can share and work on the same file with your co-authors, and you all use it at the same time. So very often, like even I do, you have co-authors logging in at the same time, and you all together edit the file you all have, make changes. You could have a Zoom discussion running on in the parallel, and then you edit the Overleaf file at the same time. So you don't end up with multiple versions of the same file, which is obviously a very terrible thing to work with. In this case, you always have an updated version of the file, and on which all the co-authors can work with. Overleaf also has a direct submission method, which, for example, if you want to submit it to the archives, you can directly submit it via Overleaf. And a lot of other journals also let you submit it directly via Overleaf. So those are the basic plus points of having Overleaf. And let's first talk about what is LaTeX. Now LaTeX, this is the only slide I'm going to show you about LaTeX, or there are two more. But basically it's a time-setting program useful for mathematical and scientific writings. And this is a very convenient guide which was used by a lot of people. Even in my times when I started off with LaTeX, I used this one. Other than that, there's a not short introduction to LaTeX, And if you actually Google on the net, you will find loads of LaTeX, guides, tutorials, etc. It's not difficult to find resources which can help you with LaTeX. So that's what you need to do. But just as an example, I'm showing you over here, what does a typical LaTeX file look like? Like I mentioned, the whole thing is basically command driven, right? So for example, you have something called a document class. So for example, if you have a document class called article, okay, there are certain packages available in LaTeX which can help you, get fonts or certain characters as you wish. For example, there's something called AMS Math, which is basically for mathematical symbols. So like I'll show you in this, here we have a single equation which we have, and that's enabled because you have the AMS Math package. Depending on the other features you use, supposing you are using figures, there's a package called graphics which you will need to have so that figures get well implemented into your file. And accordingly, depending upon whatever you are using, it's not difficult to Google and look for the corresponding package that would be there in LaTeX that enables you to have that. Now this one is very simple one. What has to be there for every LaTeX file is a begin document and an end document. If you do not have a begin and an end, it will not compile. You will get a whole bunch of errors. So this is one very important thing. One needs to be very careful about curvy brackets, for example. If you opened a curvy bracket, you have to see to it that you ended it. So what LaTeX has is, by default, it has things like sections. The other thing is, for example, if I have this section over here, I give a number to the section. If I added another section, LaTeX will automatically give it a number depending upon where do you place it in your document. So in this case, you do not have to worry at all about numbering each of your sections. For example, 1, 2, 3, 4. If you place a new one in between, it will get automatically renumbered. Same thing applies to figures, to tables, to various other things. A chapter, everything else will get renumbered as you add it onto your document, right? So for example, you have a section over here which just says hello world. And here I have an example of an equation. This is just the only equation, which over here, since you're using AMS Math package, in that, for example, if you want to write the symbol gamma, it is a slash gamma. Okay, so let's say slash gamma. This is a cap squared, which means a square, plus theta squared is equal to omega squared, right? So here I can get all these characters, a gamma, a theta, as well as an omega with a square. I have something called begin equation, end equation, and that will place my equation, right? So what you can see over here, if you don't leave any blank lines, LaTeX will continue the text, making a new paragraph. So what you see is that if I have this whole bunch of commands, the output would be something like this. So we can go back over here. Let's see, for example, here you have kept the title as title simple sample, okay? Now we have a style sheet which is there in article, which actually defines what should be the font size of the title, what should be the font size, the color, etc. And that is called simple sample, right? Now over here you can add your author name. Here I've written just my name. So you put in your author name, and it's already, as per the style sheet, it's already fixed as to how does the author name appear, which will be my name with the date. And then here I have the section, which is hello world. So you can see over here, it is marked as section hello world. So there's a numbering already given as per the style sheet, which is hello world. And I have this stuff here, and here is my equation. Since I have written begin equation, end equation, the equation gets an equation number also. But if I wish to not have an equation, I can avoid that, right? So this is just a simple example. There are lots of nuances which you can find on the net when you're doing it. So what's the difference between actually having just LaTeX running on your system or Overleaf? What Overleaf does is that it produces PDF documents using a compiler called PDF LaTeX. Okay. Now LaTeX document, when you actually make it, if you do it on your system itself, you will see that it has a whole bunch of files which it produces, right? Now Overleaf, what it does is you don't need to know the code or anything. You just edit the text, add images, and you directly see the typeset document. But in principle, if you had an overleaf on your LaTeX on your system, you can do it. But like I said, there could be version differences, etc. So to work with co-authors, it's always good to have overleaf so that you have the same version on, right? So to start, you'll go to overleaf.com. If you don't have an account, you register, start your own account, log into Overleaf and get into the system. Here, for example, I have logged in. I will show you a live this thing where you can see, I can see these are all the documents which I have. These could be owned by somebody else who is my co-author, who has shared it with me, right? So for example, if I have this document started by a co-author of mine called Rita, Rita has to share it with me so that I have permissions to edit it and I can edit it, etc. Right? And here are all my documents. And this is the view I will have of the documents. And I'll show this to you just now. On the left is the LaTeX code, and on the right is the compiled version of it, right? You also have various things like you have a history, which will actually tag in the history of what have you done with the stuff. You have a chat, and you can in that way save different versions. You can also download the PDF. It shows you errors, warnings, etc., which are there in your file, right? So what I'm going to do is now I will stop the share, and I will now very fast try to share the here I'm going to show you. Here's Overleaf, right? So I'll what I'll instead do is I will get you out over here. So this was the part that I showed you where you logged in, create your login, see your files, right? For example, I go into this file, okay, which is a book we are writing on astronomy Olympiads. And what you see on the left, this is my LaTeX code for it. On the right, you can see the compiled version. Obviously, one requirement for Overleaf is that you should have a running net. The internet has to be working. During the pandemic, often Overleaf was overloaded, but that's it. And for example, if I look at this thing over here, I can exactly mark and find the point on the code where I actually had this this thing coming. So you can see the two travelers part is coming exactly over here. I can edit it and see the output. I can see the history. I can see the chat. And another important thing which I needed to mention, which I did not mention, is because I know my time is running out, is that there is a help over here and there's a documentation. Now the documentation is excellent, which is there on Overleaf. It actually gives you very detailed help into what can you do. For example, creating a document in Overleaf, it tells you this is how you'd create your document, starting a new project, etc. For example, you want to have, let me say if you want to be inserting images, it shows you how do you insert images. This is the code. The package used is called graphics, and you will actually use this, and you'll use a command called include graphics. This is a file universe which has an image, which is actually an image, and therefore when you compile it, you will see something like this. The universe is immense, it seems homogeneous, etc. Here's this thing. So that's how you'd actually put figures and tables. You can have help on how to put a table over here. For example, if I had a table of this kind, I would do it with a begin tabular. These are centered tables, and whatever is the input for the tables. References, citations is also a very important deal of how to do use. So you can actually have a look at it. How do you actually do it? There's a package called BibTeX with which it is done very efficiently. And like I also mentioned, is that it also, when you, in Overleaf, when you are actually going on to start, if you want to start a new project, right? Click on new project. You can actually say a blank project or an example project, or here you can see the whole set of templates. For example, if I wanted to put it into an academic journal, I would actually have, I could actually choose the journal I want. You can see there are a whole bunch of journals over here, and I can exactly download the template that I need, right? So I could actually look for that, take the template I want, You could, what you are going to be doing next time is, for example, you all would be doing your CV. So you can click on resume CV, and this is a whole set of CVs which are here. You can pick up the template you like, right? You can have a look over here. There are a whole set of templates provided over here. You can pick up the template you like and accordingly, edit it and, say you like this template, you pick up this template, I click on this, I can say open as a template, and here in Overleaf I already have this document, right? So all I need to do is in this thing I can change the reading, the values to whatever I want, right? So this is the CV of somebody else, but I can adjust it to my requirement, right? So I'll stop over here, and basically it, like I mentioned, there's a lot of help available, and feel free to use that. So thanks a lot. I'll stop over here and take questions.
That was just great. This is one of those tools that's just so useful. We use it every day. It's you think back to when we didn't have it, and we're like, wow, how do we live without this great tool for LaTeX? For those of us who compiled LaTeX on our own before that. So yeah, feel free to ask any more questions in the chat, folks, and we will transition. So I'll just show the transition slide for posterity just for a moment here. And I'm going to hand off now to Anamitra, and she's going to talk about the exoplanet size distribution. Take it away.
Okay, so today this paper focuses mostly on the growth model interpretation of planet size distribution. So we know that exoplanets have a large, there's a large range of exoplanets that are there. So it has a wide range, a variety of masses and size. The sizes vary from smaller than Earth to larger than Jupiter. So this paper mainly focuses on smaller exoplanets that are there. So measurements out here, we have more than 4,000 plus exoplanets that have been discovered by Kepler's mission. So it's like here we mainly focus about the radius, which has a radius of 1 to 4 Earth radius range, and that distribution is mainly between two types, the smaller rocky planets, which are known as super Earths, and large gas dwarfs, or we can say them as sub-Neptunes. Now, the Gaia mission has shown that there is a minima in the distribution of 1.8 to 2 Earth radius, so which might be either an inherent result of planet formation, or it can be of photoevaporation of the gas envelopes. So mostly we'll see further on this, on how the whole paper discusses about the mass radius distributions, the growth models to argue. Some of the gas dwarfs are even there, which are water worlds. Okay, so the numerous things that comes up are the photoplanetary disk. Basically, have three main planet information. One can be the nebulous gas, the water ices, and the rock metals. So cooling causes, we'll learn about the cooling causes out here, the gradual condensation of various elements, like it can exclude the hydrogen and the helium things. So these different condensations that's taking place, the different condensation temperature, especially that will take place between the silicates and the ice. So which is going to lead to the planet symbols with different composition. So here we see in this the mass radius, basically the mass radius variations among the selected exoplanets that are there. So we can observe the radial velocity, the densities, which is there. This plotted data will give you the information about the radial velocity along with the mass and the x-axis. So this histogram on the right, so this y-axis shows the log bind radius distribution, and Here, the average error is around plus minus 7%. So now, what we can find is this photoplanetary disk have three. And the theory suggests us that with an accretion disk that has thermal zones that are hot enough to evacuate regions where the so in each zone we'll come out with different things, like the planet symbols are formed beginning with dust grain particles, and the coagulate, which will coagulate with the growth and kilometer size to the moon, to the mass, which ranges around to 10 raised to 5 years. So the different types of planets in our solar systems are thought to be due to different initial compositions, okay, of the silicates and the ice, but it's not yet known of this typical planetary system, about this typical planetary system. So out here, we will observe in this graph, shows that the radius gap distribution is separated between two groups of RV planets between the range of 1.4 to 1.9 and 2 to 3. So from here, this on the y-axis, we can compare the results using the Monte Carlo, this here light blue color that are there. So this shows the Monte Carlo simulations, and even the yellow color is also there. This shows the simulations which compares the results of Monte Carlo simulations. So two sets of H2O and MR curves which are there, which is different colors. The proportion of mass are calculated from the fluid system of around 300 from 1000, within the range of 1300 to 1000 feet. So on the top layer, so it is approximate, it is actually a high pressure, like it is high melting pressure. So Pebble accretion mechanism is rather used to explain how the Earth-side masses could form quickly. So next we'll come to that. So this is effective for ice pebbles only. So only a planet formed by this process must have significant portions of ice with the rocks that are there, and with most significantly the icy planets migrating nearer to the planet system, to the parent star, is mechanism the formation of the exoplanets which have a radius of 1 to 4. Hence, the model was a rocky core to which the ice or the gas is added. So that is added with the Earth masses. Next, the second type are much more massive, owing to more ice in the rocky core. So here it's suggested that in the higher cases, as we go higher, if the higher masses increases for Neptune-like planets, for which have merging ice cores. So as the icy cores themselves are less massive, before merging, the process just disrupts light and the light gas evolves. So these planets did not accrete the H and the hydrogen and the helium. So super Earth and sub-Neptunes do not have the gravity that they need to sustain. So these gases are long, hence they might either have a mechanism that can produce these gases, or are usually in an extended atmosphere. So like extended atmosphere by, I mean like they can escape. So here it can be observed like this shows this figure. This shows the stability fields of planet building materials in the protoplanetary disk of 10 raised to the power 4 bar. So this shows the condensation of the temperatures and the abundant breaking of the ice. So composition of the temperature is dependent, will always be dependent on the composition of the mass condensed phase. So finally, the conclusion we can come up 2 is that it roughly shows 4 types of exoplanets, rather not 4, 5 types of exoplanets. So rocky planets, there are rocky worlds or rocky planets, which we can see which has less than 2 Earth radius and the mass radius relations like Earth and Venus. Next, we have the water worlds, or you can say which has a radius of roughly 2 to 4, and with nearly half the mass being of water ice. And transitional planets, which has roughly around 4 to 10 Earth radius, and gas-like planets, gas giants like Jupiter. So with H and He and bulk quantities. So our own solar system planets actually fit into these classifications. So one thing is still unknown, the puzzle still remains, it's still unsolved, the compactness of the Kepler's planetary system. So which we can compare with the solar system and the lack of the planets. So these two puzzles, or rather you can say these two unsolved things, maybe you can interrelate with these things, you can solve and you can understand the initial conditions and how they form our own solar system and the galaxies, and how the structure, the migration is part is formed. That's it from the side. And yeah, so this one last thing to go with. So this thing shows that the atmospheric escape velocities versus the surface equilibrium temperature, and here it shows the density that is there, the bulk density of the planets, the super Earth and the sub Neptunes that we see out here are like that they will retain the hydrogen and the helium dominated envelopes. So that's how the whole escape velocity and the equilibrium plots is going to show. So any questions will be accepted, so free to answer them. And thank you. That's it from my side.
And Amitra, thank you so much. This was just really great. And this is really a highlight reel paper for some of the amazing work that's gone on in the last sort of 10 years, where we went from sort of knowing that we had a few exoplanets out there to really starting to understand their populations and guesses about their compositions. And it was a very nice summary that you just provided. Thank you so much for that. All right, we're going to close up our meeting today with our 2 mentor profiles. And so we have Chetan and Sunday. So Chetan, would you like to go first and tell us a little bit about yourself?
Yep, sure. So can you hear me?
Sounds good. Go for it.
Okay, so hi everyone. My name is Chetan and I'm from India. I live in New Delhi, that's the capital of India. And I'll be going through my journey and I'll try to keep it short and make it in a timeline order so that it's easier to follow, because I took a lot of diversions in my story and I ended up here after doing a lot of things that I might not have to do if I were to go straight into an astronomy path. So my story is more of a deviated path from the straight path to the astronomy. So yeah, it starts from back when we were kids and we still wondered about things looking up in the sky, like why the moon does follow us and why does the stars even twinkle. And then you see in the stars and you see some objects that are not twinkling as rapidly as the stars, and you read out about them going through the libraries and and you see that okay, the stars are twinkling, the planets are not. So that's where all of our curiosities grew from, I guess. And that's again, that's one of the things that got me interested in as a kid, looking at the sky, wondering why the moon is spherical and why the stars are twinkling and so on, some basic questions. But yeah, that did not even closely fit my goals to become an astronomer, because at that time I didn't even know that that was a possibility for me or for anyone else. So I didn't know that astronomy is a profession that you can follow. And then like fast forwarding a bit to my high school. So I took physics classes. That's where most of my interest in physics grew from. So I loved those chapters that had the gravitational bounds and everything related to astronomy. There were only a few courses that had those things, but still I was looking at those. And then I started doing an electronics and communication engineering after that. So I did my undergrads in electronics, which is a field closely related to physics, but not exactly purely physics. We had some courses in like physics and electromagnetics and so on. But yeah, it was still not physics. And that's where even that's where I didn't know that okay, I can approach astronomy as a profession. I can look at people who are through the screen. I did some courses on Coursera and so on, but yeah, it never looked like something achievable to me. And then after that I thought that I'll do astronomy sometime in my future, but I never like fixated on when I should be doing that. So I joined in as in a job in a consulting firm, and this consulting firm was even more deviated from my earlier path. So it was in pharmaceuticals. So I had clients from US major pharmaceutical companies. And what I did was basically data analysis. So I worked on SQL, I worked on Unix automation scripts, I worked on some other tools that I used in the industry like Tableau, and I even did some Python as well. So that's where most of my data analysis skills come from. And I guess these are transferable skills in astronomy because I am using them a lot in my work right now. And I have seen a lot of astronomers using them in their works right now. And even the skills I learned in undergrad. So I did a lot of work on robotics. So robotics is not exactly transferable, but there are some other things on top of that that are transferable. So I did a lot of machine learning and deep learning. And I see a lot of paper in astronomy right now that are using deep learning and machine learning to achieve many tasks. So that's where I got these transferable skills from. And then I took part in intro to Astro course. So this course, yeah, last year. So I was a participant last year, and I took the course. I worked with Joey, who is a mentor this year as well, and made a nice little a research proposal. I like got it verified by Howard as well, and that's where I got okay, I can be an astronomer if I wanted to. So that's where my journey started. So this course really gave me the ground truth that okay, we can be an astronomer, and astronomy is not just a field that's beyond the screen, and it can be achievable. So after that, I did some more work and I left my job after that. I currently am working as a research intern at Asia Taiwan, and I'm working with Dr. Alex Tichy. So I am currently working on finding exoplanet candidates using TESS. This is a common field, but we are looking at the continuous viewing zones. So as you saw in the tutorial today, there are some sectors that TESS covers. On the ecliptic poles, there are some sectors which overlap in all the sectors. So we have a lot of coverage of stars over there. So we have around 365 days of coverage for some stars. So we can identify stars which have a longer period. So that's what I am working on, finding exoplanet candidates on those particular sectors. And yeah, that's all about me. So my takeaway message would be like, I think you can try any and all things that you want. You can even try industry if you want, see if you like it, see if you don't like it. I like the industry part of it, but I didn't like the work, so I left it. And even then you can still end up doing well, I guess. Yeah, that would be all. Thank you so much. Thank you, Howard.
Thank you so much. That was very great. And I'm grateful that we were able to influence you toward astronomy a little bit. That makes me feel really good. And finally, for the end of our day, we'll have Sunday give his profile. Sunday, take it away.
Okay. It's early morning here. I know it's evening for some and day for some. Can everyone hear me?
Can hear you just fine. Yep, carry on.
Okay. So my interest in astronomy grew. I catch up with an interest in astronomy in my final year as an undergraduate in the University of Nigeria, Nsukka. Nigeria is in Africa. So it was during my project, I had a very good supervisor that actually supervised me well, and he was like a father. So he encouraged me, and most of his courses, the way he used in imparting the knowledge to me was very cool. It was a very cool science communication skill, and I understood um, everything. So most of the things. So it seems like astronomy was somehow easy for me, and I should just go into it. Though in Africa, astronomy is still developing, especially in Nigeria. Though if you go to places like South Africa, it is growing more there because of the SKA, the square kilometer array they are building there. So, but with the interest in astronomy in my undergraduate, one other important thing that helped my career in astronomy as summer schools, because still in my final year, I was opportune to attend one of the summer schools in Abuja. It's called YCA, West African International Summer School for Young Astronomers. So when I attended that, the instructors were cut across the countries, different countries like America, China, Australia, France. They came from different places. So I saw the the beauty of it and the physical training and everything. We're able to measure parallax, and it looks fun. It's so fun to do all of those things. So after that, I came back, and by then we are through with studies. So I decided to apply for several other summer schools. Some I didn't get, some I got them, and I've been into them. So though one of them I'm actually currently with is the Stone Edge Observatory that is part of Glass Education located in Sonoma, in US then. So we have been working with their telescope, making observations most times, and the kind of friendly get together, not a summer school that has a particular target like it must be 1 week or 1 month. So we always have our classes, you talk, you gist with mentors, and it keeps on going like that. If the sky is clear, you make your observations. So with them, my interest kept on increasing, like sporocketing, and one of them again, the summer schools, is this Exoplanet Introduction to Astronomy and Research. So I can say that summer schools have actually helped my life, a kind of giving me more interest in astronomy as I've been participating in them and getting more skills. So though still yet to join a master's program, but looking forward to do that soon, as I still apply to schools. So I feel summer schools are very important. So even if you have not gotten to where you want and you're still an early career researcher, you can do summer schools and increase your research skills, even if you're at home. Maybe one day you might, if you really like astronomy, you keep your passion there, then one day you might just get it and continue moving if it's what you love. Thank you so much.
Thank you, Sunday. That was just great. And I hope that those of you out there who are looking for inspiration can find some in our mentor profiles. And with that, I think I will just recap today and say that we heard some great tutorials from all of our mentors today. We heard about TESS. We got a great tool under our belt now with Overleaf. And we got some real science discussion talking about the planet size distribution. And so we had quite an amazing meeting today. So thank you all for coming. I'm going to stop the recording now and say a couple more things.